Okay, so let's go for the fourth part of this presentation. Now we will study the control of currents in rotating reference frame, the DQ control, but in this case we will not cancel the coupling terms. As in the previous part, we have considered the control with cancellation, and now we will consider the control without cancellation. Most of the parts of most of the analysis in this part are very similar to the previous one, so I will go rather quicker than in previous part. So again, we have the DQ control, but here now we are not canceling the coupling terms. So the control strategy is basically the same, but we have eliminated this cancellation. These feed-forward terms are not used anymore in this control. Again, we have here the alpha-beta components or the alpha-beta electrical circuit. And again, the regulators that we are going to use for both D and Q current loops is going to be the PA regulator with the constant or proportional gain and with the integral gain. Here again, most of the part, or at least the closed loop and the errors and so on, are working at a steady state in DC, so in DQ reference frame, and at the end, here, the actual voltages and currents are sinusoidal. And in order to do that, we need this reference frame transformation, and we need the theta angle that is taken from a PLL. But in this case, we are neglecting or the effect of the PLL. We have very similar time domain expressions for the model of the control, but here, if you remember the previous slides, the previous analysis with cancellations, we don't have the coupling terms cancellations. So therefore, they are the same, but without those two feed-forward terms. Here we substitute the step inputs, and we can obtain the Laplace domain expressions for alpha and beta converter voltages, which are these ones. Very similar to the previous ones with cancellations, but this term and this term, are different. In this term and in this term, in the previous control, the cancellation of the coupling terms appeared. Here it doesn't appear. The remaining terms, these other terms and these other terms, are the same as before. So now, if we combine for step inputs the control and the power circuit equations, we can obtain, for step inputs analysis, we can obtain the transfer functions for alpha and beta currents. And again, we have one term multiplying the D reference current, we have another term multiplying the Q reference current, and we have the coupling beta in alpha and in beta alpha. And here, as we are not cancelling the coupling terms, these two terms, compared with the previous control again, are different. In the previous terms, the filter, the inductance effect appeared, but now we don't have those terms. Again, at the denominator, we have the typical equation, third order equation that is appearing in all the controls, in alpha beta control and in both versions of DQ control. Sorry. So here again, what we can do is represent, as we did before, in this block diagram, in which we can see the closed loop control, how it's coupled. And in order to eliminate this coupling, we do the same process, the same mathematical process, which is represent these two expressions in a more compact form, and then after some developments, mathematical developments, we can achieve a very compact expressions which are decoupled. Alpha current depends only on the current reference and Q current reference, and now does not depend on beta currents, and something equivalent for beta currents. So these are the decoupling expressions. Very similar to the ones obtained with the other control, with the cancellation, DQ control with cancellation, but equivalent, but not exactly the same. If we analyze only alpha current, this first term here, and this second term multiplying the IQ here, this one, and this one, we can obtain, again, by computer software, for instance, MATLAB, and using the symbolic toolbooks, we see that both terms have the same denominator, which is here, order 6 in both. Therefore, we have 6 poles. And here we have the numerator for this first term. And here we have the other numerator, the zeros, for these other terms. Something very similar, but not 100% equivalent with the previous control, when we did the cancellation of the coupling terms. So numerically, if we apply numbers, and we are applying or we are substituting the same numbers as we have used in the previous two controls, alpha beta and DQ control, and we obtain the alpha beta frame pole zero maps applied to these obtained expressions, we realize that, again, as always, we have the steady state poles at the imaginary axis in omega, positive and negative. And now we have another 4 poles. Just remember that here we have 6 poles at the denominator, 2 here, a steady state, and another 2 with real part for the transient response or the natural response. Here we have the imaginary terms of these 2 poles are different from these ones, and also the real parts. And if we compare this with the previous obtained ones, with the cancellations, this is without cancellation, and this is with cancellation, we can very remarkably see the difference. In the previous ones, we had, with cancellation, we have same imaginary part. However, here we have different imaginary parts. And we see that we have the real parts different as well, comparing these ones with these ones. And if we compare with the DQ frame analysis that we did at the very early beginning for these controls, and with cancellation, this has to be with cancellation of the coupling terms, if we remember, we have a correspondence with the real parts of these poles and these poles. However, here, since we are not cancelling the coupling terms, we have totally lost this correspondence. So the correspondence with these ones and these ones, it's okay, but here we have lost. Basically, why? The reason is why? Because we are not cancelling the coupling terms. So these coupling terms are working or are operating as a perturbation that in closed loop produces this effect. So if we substitute step inputs at both ID and IQ current inputs, very similarly to what we did before, we can obtain very similar, equivalent, totally equivalent expressions in time domain for alpha current, for instance, only. And here again, in order to validate the obtained expressions, because we could do an error, however, we didn't, because we see an exact match between the Simulink blocks and the mathematical expressions derived here. Here is the PI controllers. Now we don't have the cancellation. Here we have the transformations of the coordinates, of the reference frame, sorry. Here we have the theta angle, and here we have the power circuit, the filter and the grid. Filter and grid. And for step inputs, we see an exact coincidence or match between converter voltages and currents flowing through the alpha beta circuits. Okay, if we do the same as we did before, but now applying sinusoidal and cosinusoidal inputs of the current references, here we have the mathematical expressions in time domain and in Laplace domain. We match both expressions of control and power circuit, but now without cancelling, without the feed-forward terms, we can obtain again transfer functions very similar to the previous ones, totally equivalent, but here these all terms are equivalent to the previous ones obtained with the cancellations of the coupling terms, and the difference is copied in the coupling itself. Here if you compare with the previous expressions, there was appearing here the filter DL effect. However, here it does not appear. So in these two terms, we can find the difference here as well with these sinusoidal and cosinusoidal inputs. These are the expressions, very the same as before. These D and Q, alpha and beta, are the same. Again, these two terms are the ones that are different. Again, in order to try to eliminate this coupling, we follow the same process as we did before, and we can obtain the final expressions, which are decoupled. And here we have the equivalent expressions, equivalent again to the step inputs with this without cancellation control, and equivalent to the cancellation, to the control with the cancellation, to the previous slides. Sorry for this repetition, but it's equivalent. The only difference remains here in these two terms. So if we apply numbers, if you substitute the same numerical conditions that we are using in the previous control, what we see now is that these are alpha currents with D affecting to D reference and to Q reference. This is without cancellation, and this is with cancellation. Again, we have the steady state in both. We have the steady state, and we have the transient response or the natural response of the poles, which are at different values in imaginary part and in real part, compared with the previous ones obtained with the control with cancellation. That there was a correspondence. So here again we have an alteration or a different location of the transient response pulse. Okay. Again, we can obtain the time domain response, very similar to the previous one obtained with cancellation. We can again obtain the body diagram, making zero the Q current input. So we only have this term for alpha current. So we are doing zero, and we have only this current reference. And what happens with the time domain response is that at the output we have these these two terms, these two currents, and these two frequencies, omega 1 plus omega and omega 1 minus omega, and the other one, these two cosinusoidal terms in this case. And in the body diagram, we see the correspondence at these two frequencies, and their amplitudes. So if you remember, we have something different, very similar, but this different with control, with cancellation of the coupling terms. We are now obtaining at both sinusoidal at the outputs different amplitudes, and this is also seen at the body diagram. Okay, so let's go with the fifth part of this presentation, which is a comparison of an analysis of the three controls that we have studied before. This comparison analysis is a summary of what you can find in the book. And later we will go for the last part, which is the future analysis. We are concluding this presentation. So comparison and analysis. Just keep in mind that we have studied three controls: the control in alpha beta reference frame, and this is the block diagram; the control in DQ reference frame, and with cancellation of the coupling terms. So we use these feed-forward terms. And thirdly, we have also seen a variant of this control in DQ reference frame, but not using the feed-forward terms. So these are the three controls. We have seen that these three controls in Laplace domain can be mathematically represented by these three expressions. I am only showing the alpha component of the voltage. For the alpha beta control, for the DQ control with cancellation, and for the DQ control without cancellation. We see the correspondences, we see the similarities and different things between all the controls. For instance, here we have first one term that appear equally in all the controls. These two terms multiplied by the D and Q references are very similar, but not the same. In these two and these two controls, they are similar, but not exactly the same. However, from here to this other control, we can see that they are exactly the same. And finally, in these two controls, in DQ controls, we have one additional term, which is the coupling term. So the beta current appears, and without cancellation, we have a rather more complete or complex term compared with the other one. And these two terms does not appear in alpha beta control. So they are similar, but not exactly the same in any of the cases. So this is the control. So this is the mathematical model in Laplace domain for the controls, and if we apply the closed loop, if we obtain the transfer functions for, this is only represented for step inputs, not for sinusoidal or cosinusoidal inputs, we see the expressions for alpha beta control, for DQ control with cancellation and without cancellation. We see very simple and compact transfer function for alpha beta control, something similar but maybe more complicated because it appears another term here and another term here that does not appear here. Here we have the coupling, the beta dependence to the beta current in alpha current. We have seen a procedure to obtain the coupling currents for these both controls, and we know that we can obtain the coupled transfer function for alpha and beta currents, only here is alpha current represented, which is equivalent in these two controls, but not exactly the same. The poles and the zeros from here to here in these two controls are a little bit different. Equivalent expressions, but not exactly the same, and give us different poles and different zeros. And this is for step inputs. Something very similar we obtain for sinusoidal inputs, but here I'm not showing it. In the book you can find this summary more complete. And finally here we can see that from this transfer function, when we substitute the step inputs, we can obtain the time domain expressions for all the controls. Here only, again, alpha currents are represented. So here we see terms multiplying to ID and terms multiplying to IQ. And something similar here, and something similar with this last control that we have analyzed. Here we have a real pole only, and here we have a complex conjugate pole, and here we have the steady state expression, and something equivalent here. However, in these two, we have these two terms, which is the transient response applied to the reference, and these two terms are the transient response or natural response, and these two terms are the steady state response. The exponential terms are made zero, and something very equivalent, very similar with this control. But obviously, as the transfer function have different poles and zeros, the expressions are equivalent but numerically different. But here in this summary, in this table, you can see the similarities and different things between all the controls. Finally, if we do time domain responses for step responses under same conditions in all the controls, and we apply 1 ampere at both D and Q components of the current references, we can see the voltages, currents in alpha beta, and the natural responses for all the controls. There are not big differences, so it's not easy to find the difference here, but if we check the natural responses, we see how different it is, or they are the transient responses or the natural responses. However, the steady state are equal. These parts is the steady state, and the transient for this control with cancellation or the natural response is extinguished in shorter time than in the other two controls. The same, but if we obtain the DQ current, the DQ currents obviously expressed in DQ reference frames of these controls, here is what we obtain. So these are the same currents, these currents, but represented in DQ reference frames. So they are the same currents represented in a different reference range. And here is what we obtain. Again, the shortest natural response is obviously achieved with this control, with the same conditions, with the same numerical conditions in all the controls. I'm not saying that this is going to achieve always the same, the shortest transient response. Probably by changing numerically the gains of the regulator here, we can obtain something quicker, similar to this, and with this control as well. But under the same numerical conditions, this is what we obtain. Okay. Finally, if we analyze the poles for the three controls and the frequency response, again, under the same conditions, here are the poles for all the three static controls. Here we have the steady state poles, which are the same in all the cases. And here we have the transient response poles, which are different in all the cases. And all these transient response poles are related to, or are the responsible, combined with the zeros, with these natural responses. Finally, the frequency response or the body plots are located here, are shown here for all these controls. It is quite curious that for the same frequencies, the same poles, the same gains are achieved in this control and this control. However, this is the only control that achieves the same frequency, the same amplitudes for the different frequencies. This and this at different frequencies obtain different gains, and this obtains at different frequencies the same gains. There is a curious things that happens. And for final analysis, we can show how changing the gains of the regulators, again using the same numbers in all the three controls, how the poles are modified by changing the Kp and Ka. And this is how the poles and the zeros are modified in all the controls. This is the tendency. So here, with this, we can see how by changing the gains of the regulators, we can make the system more stable or more unstable. By checking, for instance, how close we locate the poles, the transient response poles, to the imaginary part. You know that this is the unstable area. So here we see the tendencies. For all these cases, we have an equivalent behavior in yes, an equivalent or a consequence in the time domain. They are all connected, and here we have how they change the step responses, and these are the alpha currents also shown here. So the shortest step response, the transient response, is still, as we have seen in the previous slides, for this control. And finally, here you can see how the body diagrams change. Okay, so to conclude, let's go to just shortly mention some possible future analysis that we could do with these mathematical model equations in alpha beta reference frame. And just some ideas in this last slide could be that we could also analyze what happens with different topology of filters, for instance, including a capacitance, an LC filter or an LCL filter, or other combinations that you can find in the literature. With this mathematical equation, it is represented in the book, but it's not. I haven't presented in this presentation in order to don't do it too long. You can also include delays of filter that we normally use in the control and see how are their effect on the stability, therefore in the poles and in the zeros and in the time domain responses and so on. We could do also the analysis in weak grids, in which we have an equivalent impedance that could be considerably high compared with the impedance of the filter that we are using, and we can also do this analysis by applying these mathematical equations. Again, in the book, it is analyzed. In the book as well, we are also analyzing the PLL dynamics, include the dynamics of the PLL that we are using in the control, and analyze and study how it affects to the control loops. It's quite interesting. And for future analysis, this is not analyzed in the book, we could also study how different converters with different current controls could interact between each others with this mathematical framework. Could be quite simple to do. Also, we could do analysis under parametric uncertainties, for instance, when we are using a complex filter topology and we have uncertainty on the values of them, and etc. We can also study many other things with this mathematical model that we have developed in this book and also in this presentation. So that was all. I hope this presentation was useful for you. Thank you for your attention.